Hello everyone, I'm Minmei Wang, advised by Professor Chen from University of California, Santa Cruz. I'm really glad to present our work, Vacuum Filters. The other co-primary author is Mingxun Zhou, who is from Peking University. Approximate membership query data structures rely on space-efficient, probabilistic data structures to test whether a queried item is in a large set of items. These data structures are widely used in different applications, such as Google Big Table, Bitcoin, packet forwarding application. Some examples of the AMQ data structures are bloom filter, Cuckoo filters, quotient filters, and so on. One of the most popular AMQ structure is Cuckoo filter. This figure shows an example of the twofold Cuckoo filters, which consist of a number of buckets. Each bucket has 4 slots. Cuckoo filter is fast, dynamic, and compact. Besides O1 lookup, deletion, and a compact memory cost, it also supports amortized constant time for insertion. For any item X, it has 2 candidate buckets, B1 and B2, to store its fingerprint. However, there are 2 main limitations of Cuckoo filters. First, the advantage of memory efficiency is achieved in ideal situation. The right figure shows the bits per item, varying with different number of items. We can find that in the worst case, Cuckoo filter requires almost twice as much memory compared to that in the ideal situation. The reason is that Cuckoo filter uses XOR operation to calculate the alternate buckets for each item, which requires the number of buckets m to be a power of 2. This may waste the memory with some number of total items. Second, Cuckoo filters do not support dynamics with incremental expansion of the item set and duplicate insertions. To overcome the 2 limitations, in this work, we first propose vacuum filters. It costs the smallest space among all known methods when the false positive rate is smaller than 3%. The figure shows the comparison results of the vacuum filter compared to Cuckoo filter and the bloom filter. We can find that vacuum filter achieves the best performance, and the performance is stable, varying with different number of items. Also, vacuum filter achieve good performance in throughput. We then propose an instant updates and a periodical reconstruction method to deal with dynamics. We first talk about the design of the vacuum filters. We begin with an observation. If we group L buckets into a trunk, and we limit that the 2 candidate buckets of any item are in the same trunk, we call the length of the trunk L as the ordinal range. We find that with the large ordinal range, the filter can provide high load factor but bad flexibility and bad locality, while with a small ordinal range, the filter provides good locality, good flexibility, but low load factor. So, can we combine the advantage of large ordinal range and small ordinal range to overcome the first limitation of Cuckoo filters and also achieve a good throughput? The answer is yes. In this paper, we present a new multi-range ordinal function. The basic idea is that items have independent ordinal range. Instead of using a same large ordinal range in the Cuckoo filters, most items use small ordinal range, and a small fraction of items use large ordinal range. Now, the challenge are how to determine the number of ordinal range and how to decide the length of each ordinal range. Assume we use 2 ordinal range, L0 and L1. 25% items use L0, and 75% items use the much smaller ordinal range L1. We design a range selection algorithm to calculate the ordinal range. In this algorithm, we can first model the problem as the balls into bins problem. After knowing the total number of buckets m and the number of items that use the ordinal range, we can estimate the maximum load for any trunk. According to the theoretical analysis, think about it. If we can find a smallest L that makes the estimated maximum load is smaller than the capacity of each trunk, we can accept this ordinal range as the required one. This range selection algorithm provides an upper bound for the required ordinal range. So we first calculate L1 using the range selection algorithm by specifying that 75% items use this ordinal range. Then we calculate L0 by using the range selection algorithm by n items, because we find that large chunk with L0 and small chunk with L1 may overlap as shown in the figure. To decide the number or ordinal range, we do experiments to show the performance. We find that with 4 ordinal range, the filter can achieve a good trade-off between the higher load factor and a good data locality. So in our design, we adopt 4 ordinal range. In summary, with n items, in the first step, the filter will compute the number of buckets m, and then it calculates the 4 ordinal range automatically from L0 to L3. For any item x1 that needs to be inserted into the vacuum filter, it needs to first randomly pick an ordinal range, such as L1, and it calculates the 2 candidate buckets B1 and B2 based on the chosen ordinal range L1. We also propose a new insertion algorithm to achieve a higher load factor and a better insertion throughput. The details are in our paper. To deal with the dynamics, we propose an instant updates and a periodical reconstruction method. This method can be applied for any of the MQ structures. It maintains 2 processes. The lookup process is in the fast memory, which supports lookup and instant MQ updates. However, after a period of time with a number of updates, the structure may be suboptimal. For example, the size doesn't fit the current item size. So we introduce another process called construction process in the slow memory. It maintains the full item set and periodically reconstructs the MQ structure. Then, the new version of the MQ structure will be installed in the fast memory to replace the old one. Our proposed IUPR method can make the structure in its optimal condition to provide a better performance. In the evaluation part, we evaluate the memory cost and throughput. We run experiments in a Dell workstation with 30 megabytes L3 cache. We compare our proposed vacuum filters with most of the existing MQ data structures. We also evaluate the performance of the dynamic system with IUPR method. This table shows the performance of space and the lookup throughput of different MQ structures. We set the result of blown filter as the baseline. We find that vacuum filter achieved the best performance in both space and the lookup throughput. This figure shows the overall insertion throughput. We find that vacuum filter outperforms Cuckoo filter and any other MQ structures except the block blown filter. We also evaluate the performance in the SSD hard disk. While the memory access speed is much slower, we limit the memory to 100 megabytes. The figures shows the insertion and positive lookup throughput, varying with different table occupancy. The results show that vacuum filter outperforms Cuckoo filter due to its better data locality. These results show that our proposed vacuum filter can achieve a better performance compared to other MQ structures. More experiments are in our paper. Please refer to the paper. We also evaluate the performance of our proposed IUPR method. This figure shows the lookup throughput of the system with IUPR method compared to the system without the method. We can find that with periodical reconstruction, the system can achieve a better lookup throughput because the structure is in its optimal condition to provide a better lookup performance. In conclusion, vacuum filter is memory efficient. It costs the smallest space among all known methods when the false positive rate is smaller than 3%. Vacuum filter can achieve good insertion, lookup, and deletion throughput. Our proposed IUPR method can perfectly handle the dynamic environment. Our code has been published on the GitHub. Welcome to use it. Thank you.